Mr. Vincent. Thanks for joining.
Good evening, sir. How are you, sir?
I'm good, thanks. Looks like I do not know
Hello?
whether. Yeah, I'm good, sir. Thank you. Thank you for joining. We're going to wait for 1 more minute for people to join, as well as the speaker, Ajay, is actually setting up his audio.
Could you hear me, sir?
Yeah, I can hear you.
Okay, I think this works. Everyone can hear me now, right?
Yeah, yes, Jay. Okay, let me see how many. Yeah, we are expecting more people to join, and also people from the panelist side, people have to join. But in interest of timing, let's get started. Hold on. Okay, good evening to all of you. Thanks for joining this webinar. And it is my pleasure, having you all here. And also we have, special panelists from institutions as well as, organizations. And also I have speaker from Ajay. Ajay, who is actually doing his undergrad in UIUC. And today, as part of today's webinar, Ajay is going to be presenting about the NLP features and how he has been working with the IBM system as well as many supercomputers to develop the NLP related solution. This is going to be an interesting webinar, and also there will be a questionnaire where you guys can participate at the end of the session and the end of the webinar. And certainly, the first three people who are answering the quiz will be awarded, with the T-shirt, and also definitely, acclamation and the appreciation also. With this, I also would like to introduce, the panelists here. I have Dr. Priya from LIT and Dr. Vincent Anthony from PSNA. And I'm expecting a few more panelists to be joining as part of this webinar. Ajay, go ahead and start your presentation now.
Okay, yeah, thanks for the introduction. And let me see if I can first get my screen share working. Okay, cool. So yeah, hi everyone. As Ganesh just said, I'm Ajay. I'm a student at the University of Illinois at Urbana-Champaign. I'm also, founding member of this small research group called Landscape AI, where we do all sorts of interesting deep learning research stuff. And I'll talk a bit more about my research and what we've been doing, using the amazing compute capabilities of the IBM power systems towards a bit at the end of this talk. But before that, what I wanted to do is, really talk a lot about NLP, the state of the ecosystem today, what the state of the art is, and really how the field has progressed a lot in the last few years. So, I mean, just to start things off, one thing I really want to get across is that the field of NLP has gotten really good in the last few years. So just to, I guess, demonstrate that, let's take a look at this quick little app over here. This wasn't made by me. This is actually a fairly popular app. Some of you might have heard of it, but I just think it's interesting to see. So let me first just quickly demonstrate it, and then we'll, talk a bit more about what the implications of this thing are in a few moments. And this might seem like, a very silly, simple game, but actually this, this simple project utilizes one of the most important new developments in NLP, which is very large pre-trained language models. So, I mean, enough about that though. Let's just get on with this small little demo over here. So this little game is called AI Dungeon, and it's built around this previous, this general idea of this category of games called Dungeon, where, it's like a text-based adventure sort of thing. Back in the day, you'd have like simple rule-based, dungeon games where like you'll be given a different scenario. Like for example, you might, the text prompt might say you go in front of the room and there's, two doors. Do you take the one on the right or the one on the left? And depending on the choices you make, different things will happen and the story will evolve. So that's the regular dungeon, but this is like a new evolution of that for the 21st century. And over here, it's the actions you take are actually entirely up to you. So here's what I mean by that. I'm just going to choose a random one of these demo scenarios over here. And let's see. I'm not sure what exactly this is, but let's just select it and see what happens. Okay. So soon I'm going to be provided with a text-based prompt once this loads. And essentially what I'll have to do is just narrate, whatever I want. So over here, they have this small, text-based prompt. There's nothing special. Anyone can write a simple story, right? But here's the interesting thing. Over here, I decide what I want to do. And the system actually reacts to this in real time. So all this text over here wasn't actually written by a human. Well, actually, in this case, I'm not too sure how, the initial prompt is made. But the idea is that all these replies are based on, what I do over here. So over here, I said I move forward, and then it says, okay, something happened, and you arrive at the door. So I open the door. And as you can see, the system is actually able to interpret the commands I'm typing in here, and all these things that I'm typing. These aren't any pre-configured things. This is all like happening in real time. So this is almost as if I'm talking with a human or a game developer who's actually kind of laying out the story and planning it in real time. So all these sorts of interesting scenarios tend to pop up. So okay, let's see. It says I see wood, stones, and other building supplies. So let's see. I move the wood. I'm just coming up with a few random things over here. I haven't really planned this before, so I'm not sure what's going to happen. But as you can see, the system is able to come up with not just coherent sentences, right? Like it's impressive when machines are able to come up with sentences that sound reasonable to a human being when in their entirety. But the system is actually able to pick up on the actual semantics, the actual meaning of the sentences I'm typing, and it's able to react and sort of build up a story in real time, right? So over here, it's able to understand that I wanted to move the wood, whatever that means over here, and it says I pick up the piece of wood, throw it to the side, and it's kind of just building on whatever I'm saying and happening in a very organic, natural way, as opposed to the previous versions of the regular text-based dungeon, where it is all based entirely on rules. If you meet a door, you can only go right or you can only move left. Over here, I have the freedom of natural language. I can type pretty much whatever I want, and the system is going to react to it in some way. I mean, garbage in, garbage out. So if you type something that doesn't make a lot of sense, you're not going to get a reasonable answer. But yeah, what this really demonstrates, though, is the incredible progress NLP has made over the last few years. So initially, when this particular demo came out, it actually started with this old model called GPT-2, which is released by OpenAI. They're a very big, very popular, famous research organization. And originally this demo was kind of just like a fun little thing that researchers used to play around with. Instead of always staring at training scripts and seeing Jupyter notebooks all day, it was nice to see the models you build actually deployed in some sort of a setting, regardless of how silly that might be. And it was cool to see the results kind of come to life. But over time, this this particular app has gotten extremely good. And actually now, this is much more than a demo. This is like an actual real company that's actually building real things. So it's available on both the iOS and Android Play Store. And this company Latitude has actually gotten a lot of funding to develop new sort of systems that progressively build new game worlds and environments. I'm not sure exactly what they're doing at the moment, but this has actually become a fairly big thing. And I think what this demonstrates more than anything is that NLP now is good enough to move outside of the research lab and into the real world, which is what Latitude here has demonstrated. And there are a lot of amazing other examples. I just wanted to point to this one in particular because it's something that's actually being deployed, funded, and used. There are also many incredible demos. If you check out OpenAI's Twitter account, they have demos of GPT-based models writing code. So you kind of supply a text-based description, natural language description of what you want a website to look like. For example, you could say, I want something with a red button that points to this URL or something like that, and the system actually is able to generate HTML code that that has a pretty good approximation to what you describe. So GPT-2 has been used. GPT-2 and even more recently GPT-3 have been used for a lot of interesting things. But perhaps more interestingly is all this stuff that I'm talking about, GPT-1, 2, and 3. All this happened in the span of like less than 5 years. So you can see from the chart over here that way back in April 2018, just essentially 2018, the specific month doesn't matter. But back then we had really small models. So over here it was 94 million parameters. If you're not too familiar with machine learning and deep learning, all I can tell you is 94 million is not very large by today's standards, but it's what we started off with. And like not too long ago, this is very recently, we were doing simple things like text classification on IMDb, or simple named entity recognition, or the Stanford Squad question answering database. And we were just doing NLP and all these somewhat restricted researchy type questions. And the goal is metric maximization. How well can you get your classifier to perform in terms of accuracy? All the traditional metrics. And that's great. But what we saw from then is that really something magical happened, and the field of NLP took off dramatically. And you can see the sort of exponential progress. In fact, with stuff like Megatron, it's even greater than exponential. And this trend isn't even dying down. So you might have noted that the graph over here is gets cut off in July 2019. So I haven't made this particular plot myself, but we're currently almost nearing July 2021. So this is almost like 2 whole years of progress that have been built on top of this. And since then we've seen incredible things like OpenAI's GPT-3, which isn't listed over here. We've seen Clip and DALL-E. Those are again a few experiments run by OpenAI. And in general, I think Hugging Face, which is a company in a deep learning library package framework that I'll talk about a bit later. But Hugging Face is really democratized a lot of this stuff. And now it's practical for anyone to really train extremely complicated, what would have been extremely complicated language models and NLP systems a few years ago. Very simply, just with a few commands on the command line. No need for any complicated math, no need for a PhD, and any of that stuff. But we'll get into that in a bit. The first thing that I really want to drive home here is that it's the whole progress curve over here. It might look kind of daunting and spectacular, but it's actually at this point it's extremely simple to actually use all of these language models today. So, and then the reason that's true is because of something magical called transfer learning. So this is probably the single most important new idea across the field of NLP. So, I mean, probably not as much as all the other things that have happened in the past, but definitely I think in the last maybe 4 or 5 years, transfer learning is one of the single most important things that has led to this progress curve shown over here. And pretty much all these models actually are now fairly commonly used in transfer learning scenarios. So what transfer learning is, in case you guys aren't familiar with it from computer vision, is generally it's a technique where put simply, a large organization, a large team, like OpenAI, like Facebook, like NVIDIA, as most of the players on this plot are, like all these people, big research labs, pour in a lot of money and they invest heavily into building these very large language models. So a language model is simply, it's a form of a deep learning model that's trained to predict the next word. So similar to the AI dungeon example we saw over there, in a much more, I guess, limited setting. So you given maybe a sentence or two sentences or something like that as a prompt, and it'll continues to just keep generating new words, and ideally those words are supposed to make sense. So that's how the language model is. It's a fairly conceptually simple algorithm. All you have to do is, given a sequence of words, predict the next word. That's all the language model is, and that scaled to infinity, basically, with a lot of money, a lot of GPUs, a lot of compute, has really driven the field forward. And the best part is, with transfer learning, what you can do is you can take these models that Microsoft, that Facebook, that OpenAI have already trained, and you can kind of work on top of them. So you may not be interested in just predicting the next word. Maybe you're interested in text classification, which is actually an example we'll look at in a bit. So maybe you're interested in text classification. In that case, predicting the next word is not that is not that useful. And also, text classification is also a somewhat limited problem. It's much simpler than predicting the next word, right? So given let's just say the IMDb movie database, that's the simplest example. Predicting whether a review is positive or negative is conceptually similar, simpler than learning to predict the next word in the English language, which is fairly large and complicated. But with transfer learning, the second problem, doing text classification on IMDb, stuff like that has become extremely simple. So transfer learning, again, is something that wasn't that easy, even like 6 or 7 years ago, but now it's extremely simple and you can get started right away. And I mean, like now, so we're gonna actually take a look at a demo of transfer learning and what it can do. So over here is, I've opened what's called a Colab Notebook. If you guys aren't familiar with it, again, Colab is sort of an environment where you can, just give me a second here. So Colab is an environment where you can, essentially run Python code in a collaborative way. So you can, share these notebook files with others. And I guess I can share this in the chat too, just so that everyone can follow along if you want to. Okay, let's see. Yeah, so I just shared a link with the notebook, and so if you guys want, you can follow along right now. But that's not strictly required. So over here, what I'm doing is I'm gonna run Python code interactively in this Jupyter notebook-like environment. This one is Google has launched a service, and it's fairly simple. You just follow the link and you can start running Python code right away. And what I would show you is that using this, essentially, this is a free environment. Anyone with an internet connection and a laptop can access Google Colab just by following the link I shared, honestly. And what I'm going to show you is that transfer learning is extremely simple. Using libraries, of course, is we're not going to implement everything from scratch, but I think that's the important thing. So a lot of these open source libraries, I think in particular, FastAI, Hugging Face, and Spacey have made it extremely simple to do extremely complicated NLP things. Not just NLP, in general deep learning, but in this case, what we're going to look at is NLP specifically. So these libraries have made NLP and deep learning extremely simple, and to the point where anyone, like I said, can run it for free on an environment provided by Google, and it's just essentially a few lines of code, all written in Python. It's doing complicated stuff behind the scenes, but we don't need to worry too much about that. And what I'm going to do now is probably not wait for every single block of code to run, because this particular notebook has the results populated. So I just want to quickly go through some of the code examples here, just to show you at a high level what transfer learning is, how it works, and things like that. So like I said, in this example, we're going to use FastAI. Another extremely popular library is Hugging Face. And I'll talk about that in a bit. I don't think we're going to show a demonstration of Hugging Face transformers today, but it's an amazing library. You should check it out. And I'll share a link for that in just a second. But yeah, so this particular notebook is, like I said, it's already been run once and the outputs are saved. So let's just take a look at this and see what's going on, right? So FastAI is this, it's an open source deep learning library, made by Jeremy Howard, Silva Gunger. There's a few people involved in it. There's a whole team now. But yeah, FastAI is essentially a high-level wrapper on top of PyTorch. PyTorch is another deep learning library. This one is by Facebook. And FastAI provides, a lot of functionality that makes it extremely simple. Just do like, the most common things that you might do in, an NLP or a deep learning pipeline. So things like, downloading the data, extracting it, and, creating data loaders, creating, making data accessible by a deep learning model. So all this stuff FastAI automates, makes extremely simple. So it's just a few lines of code, as you can see over here. I'm not going to go through the, all the details of this, but you can download the IMDb dataset using just like one line of code, extract it, take a look at the dataset, and within a few lines of code, kind of abstracting away over some of the details, we have a batch of data. A batch is the fundamental unit of what you'd pass into a deep learning model for training. And it's essentially just groups of data. So the entire IMDb dataset, I think, contains about I think 6,000 examples, something like that. Each example looks something like this. So there's a text-based review that some critic has posted, and then there's a classification for it, whether that review was positive or negative. So over here there are a lot of strange-looking symbols. XX mage, XX unk is another one, XX up. So I'll explain a bit about what these symbols mean in in a few minutes. This is due to a process called tokenization. But I think more importantly, the idea is, within a few lines of code, we're able to visualize our data, get a sense of what's actually here, make sure that nothing's wrong, make sure that that some of these examples at least make sense, and that we have categories for training a model to classify on. So the first thing that we need to do over here is train a language model. But it seems like what this particular notebook is doing instead is actually just training a text classification model from scratch. So let's begin with that. Again, I don't want to spend too much time on some of the details that are easy to find online, probably not too relevant to the point I'm trying to make. But just so you know, this particular model is based on something called AWD-LSTM. This is a particular deep learning model based on the idea of recurrence. It's somewhat old at this point, but I think it still works reasonably well. And but more importantly, what FastAI allows you to do using this AWD-LSTM model definition is build a text classifier extremely quickly. So this is literally again one line of code. You add in a few parameters. They're not too important at the moment. You say that you want to get accuracy, and then you start the training process with learn.fine tune. So this is again is doing a step called fine tuning. If we don't need to be worried about too much more what fine tuning means at the moment, but instead what we can also do is learn.train. Those two things are almost the same thing. But what's happening over here is that in FastAI, we're defining a text classification based learner. So this is a model that's going to do exactly this job. It's going to read in all these words somehow, and it's going to make a prediction. And the reason I'm abstracting on top of all these details, like how exactly do you pass these words in? How exactly does the model make a prediction? I'm not focusing on all those details now because I think it's important to get a high-level perspective first. So, essentially what they're doing is they're building this learner, right? And it's based on something called AWD-LSTM. We don't need to know what that is, but it's going to classify text. So that's what's important. And eventually what we're going to get out is an accuracy score. So we want to see how well the model is doing after it's been trained on to do this task. And using just a few lines of code, we're already able to get like 93% accuracy. Using just FastAI defaults, just plug in a few numbers over here. This is a fairly straightforward demo. Like I think all in all, it's been like less than 10 code blocks since we've started this whole thing. And of course, I encourage you all to actually try this example yourselves. It's all this is in a real runnable environment. So this isn't just like some research paper where people are posting tables. Like you can actually run this code. I don't want to do it now because it would mess up the results. So these outputs would get cleared if I actually run this cell. But you can do it in this in this case, I didn't actually import and run all the things above. But and also these code cells take a few minutes to execute, so don't want to do it live here. But yeah, essentially, if you do decide to run this yourself and you try it again, you'll see that you'll also get something, maybe not exactly 93, but something close to that. And I think that's pretty cool, right? Using a fairly simple dataset method. This isn't some sort of complex web scraping thing. People have made this dataset open to the public. FastAI has made it easy for you to download using a few simple functions. You can look all these up in the documentation. It's fairly well. It's a fairly well documented library, and they have all the necessary details. But you can do all the stuff fairly simply and get reasonably good accuracy extremely quickly. And here are some of the results of that. Again, if you want to scrutinize this, you can check out the link with this notebook, and it has all the details of all the details, all the code, and you can run this yourself just to verify that this isn't some sort of a fake result. But I think what's more interesting is this was possible maybe 4 years ago, right? This isn't anything particularly interesting. Like I don't think AWD LSTMs existed 4 years ago. I might be wrong on that, not sure. But this is a fairly standard NLP pipeline from like 5 years ago, right? You get your data, you do some pre-processing, which FastAI over here is abstracted that away. But you might want to do some pre-processing, tokenization, which lets you come up with these characters, which I'll explain later. And you fairly standard process. From there, you define some parameters, you train your model, and you get some accuracy. This itself isn't particularly special or surprising. But what the new approach is a little bit more nuanced. So I mentioned before that we have these things called language models that are growing exponentially in size, and it makes sense to leverage all the work that Google, Facebook, Microsoft, OpenAI, what all these people are doing. It makes sense to leverage their work instead of starting from scratch. So over here, what we're essentially doing is starting from scratch, right? You take an AWD LSTM and you just train it, and it does reasonably well. But instead of that, like, why would I want to train my model entirely from scratch when there are people who've already trained a model that can do a much more complicated problem, right? So Wikitext over here is a very popular NLP dataset. It's essentially a large portion of Wikipedia. And yeah, it just contains a lot of Wikipedia articles, right? And just think about it. A language model, like I said, its job is to predict the next word in a sentence. So which one is, easier? Classifying, simple positive and negative, movie reviews, or actually predicting the next word of a Wikipedia article? I think it's fair to say that the Wikipedia language modeling is significantly harder. And if you try, training these networks yourself, you'll see that too. In general, you're going to need a much larger model to actually predict the next word on Wikipedia. It's going to require more compute, all that stuff, right? But it's complicated. But the good thing is people have already taken care of this stuff for us. So OpenAI has already trained a very large language model. Google has already trained a very large language model. So this step is essentially already done. It's automated. The big players have already taken care of this in some sense. And now here's where you come in. You want to do text classification on IMDb. So you don't really care about Wikitext. You don't need the Wikitext dataset. So you're starting at this stage. So you have a trained language model. And what you're going to do from here is you're going to fine tune that language model. What that means is, you have the language model and you're going to do some more weight updates. So the language model is, it's a deep neural network. I'm assuming that you guys have some familiarity with machine learning concepts. That's kind of, most modern NLP techniques, do require some form of deep learning. So yeah, I'm assuming that this is, you guys are somewhat familiar with the general idea of deep learning, the idea of a neural network, that you have parameters and you update them. If not, all I'll say is that the most important thing, one of the important things in a neural network is the number of weights, so the number of parameters over here. So in general, the more parameters you have, that means you have a better neural network, means you have a network that's capable of making more complex predictions, right? So we have a large language model from Google, and what we're going to do is fine tune that to predict not Wikitext words anymore, but the next word in the IMDb dataset. So we have the IMDb dataset here that has a bunch of words. You know, and what we're going to do is we're going to say, look, I don't really care about what the category is for now. I'm not concerned whether these reviews are positive or negative. All I want to do is, you know, sort of read this text over here and try to predict what the next word is in IMDb itself. So IMDb has, you know, like I said, 6,000 samples, right? So they have 6,000 samples of what the language looks like. And what you're going to do now is fine tune your language model such that it predicts IMDb words instead of predicting Wikipedia words. And from there, what we're going to do is, you know, make a small modification to the network after that. And then finally fine tune it so that the model is no longer a language model, but it's a classifier. So if you want to know the details of how you convert a language model to a classifier, all the details are in the code over here. It's also documented in the FastAI library. I'm not going to talk about too much of that now. You know, that's kind of a minor thing. But you know, let's just take a look at the results and see what's actually going on over here, right? So there's a bunch of code over here that's used to set up the language model learner. Again, it's documented in FastAI, so I'm not going to cover it in too much detail. But yeah, essentially above we had what is called a text classification learner. It, you know, used in AWD LSTM. It's a similar setup over here, except we're going to train a language model learner. So language model learner is something that's going to, its job is to read in all this text that we have over here and try to predict the next word if you, you know, let's say hide away a portion of the sentence. So this is the task that, you know, it is being trained on. And you can see it's, you know, let's try, you know, training it. And it doesn't seem to perform that great. But actually 29% accuracy is impressive if you think about, you know, just the size of the English language, right? Just think about how many, you know, millions of words. Actually, I'm not sure what the scale of the entire English language is, but if you just, you know, take the number of words that are in the English language and then just do, you know, 1 divided by that, that's the probability that, you know, if you randomly choose a word, you get it correct. So it would be 1 over, you know, like, I don't know, something like on the order of millions, right? And compared to that, this language model is able to predict the correct word about 30% of the time. And that's very impressive because, you know, there are also many variants of words and all these things. So, you know, for example, like over here, if the word that needed to be predicted was attempt and instead you predicted, you know, try, that might be, you know, these were the synonyms. So maybe it's acceptable to have them, to, you know, to have one instead of the other. So this is, you know, this accuracy metric is not the most important thing, but it gives you a sense of how good your language model itself is doing. But again, we don't care about how well the language model is doing, right? Remember, our goal over here was to build a text classifier on IMDb. So, you know, at this stage, we downloaded the language model from, you know, whoever trained this large language model over here. It's trained on Wikipedia. We don't have to deal with the complexities of training on a massive data set like Wikitext 103. We're just looking at IMDb. We've trained a language model right now. So we now have a model that can predict, you know, the next word given in an IMDb corpus. And this might be slightly different, just intuitively, this might be different from Wikipedia, right? So the type of text you'll see on Wikipedia is generally different to the type of text that you might see in IMDb. So this step over here is, again, a little bit more training of the language model. It's, you know, a few steps, again, documented in FastAI. But we're able to get the, you know, IMDb language model up to 34% now. And, you know, this is just a quick demonstration of what's going on here. So, you know, given this prompt, I like this movie because the model is able to now predict, it's able to come up with a compelling movie review sort of thing, right? So over here it says, I like this movie because of its story and characters. The storyline was very strong, very good for a sci-fi film. And that sounds like reasonably, you know, it sounds a little odd, but it's almost there. This sounds like something you might see potentially in IMDb, right? And over here, you know, there are a few grammatical mistakes. It doesn't sound, you know, that perfect, but the model is able to come up with some reasonable sentences over here. And so, yeah, that's, you know, step 1 of the process. We downloaded the language model that was trained on Wikitext, you know, fine-tuned it so that it does well on IMDb. Now we have a model that can predict the next word in an IMDb corpus. And now we're going to do this magical process that converts a language model to a classifier. It's not magic. You look it up in FastAI documentation. But essentially, this is the code for that part. We load the language model that we trained previously, and we make some modifications to it, and then we can finally fine tune the entire model. And what at the end of the day, the important thing is we now have 94% accuracy on IMDb. And going back to the original example, like how good was this thing without transfer learning? Over here, if you recall, it's about 93, right? So you might think, oh my God, it's just 1 percentage point. It's not even that big of a difference, but it actually is, and it's not that obvious with this example over here, because like most of the time in practice, you don't get 94 or 93% accuracy on your first try using uh, a simple text classifier. That is generally very hard to do, and it's a rare thing. But with the power of transfer learning, it actually is kind of simple. So you make less changes to your code. You work off very well established baseline, and use a fairly well established process at this point to come up with a model that performs much better. In this case, that huge performance boost, like I said, is not that clear, since we already had 93% accuracy, and it's hard to get much higher than that. But in general, transfer learning is really powerful. This entire process in general allows you to come up with much better models much faster, and lets you focus on things like actually solving the problem you're interested in and deploying a real world solution, as opposed to just like continuously tweaking parameters and figuring out what learning rate you have to use and what optimizer you have to use, and whether you have some complicated bug in your code due to the dimensionality of some tensors. And it kind of simplifies all that process, because you don't have to make your own model. You just download a language model that has its own specific definition. This model is well established, so you don't need to worry about the architecture. You don't need to worry about having too much data, because this is trained on the entirety of Wikipedia already. You don't have to worry about training, because and setting up a complicated distributed training pipeline, because OpenAI has already done that for you. And so whereas previously, in like 6-7 years ago, we were starting from here and we were expecting models to do extremely good, and that wasn't really working out. So NLP was reasonably okay, but it wasn't the most popular field in deep learning, and certainly wasn't as big as it is today. And really, it was this process of creating a large language model, fine-tuning the language model, and from there fine-tuning on what's called a downstream task. So here we're doing classification. This can instead be question answering. It can be named entity recognition. It could be whatever you want, right? The task is up to you. But this new process, transfer learning, is really what made NLP so successful. Okay, so that was cool and all, right? So it's nice to see, a few lines of code, a model gets trained, it performs really well. All that's nice, but it's since we care about actually understanding what made NLP work. I think it's important to also look at the low-level details. So now what we're going to do is kind of walk you through step by step what the general pipeline is in a modern NLP setting. So the first thing is tokenization, right? If you want your model, if you want a computer to be able to read text and do something useful, the first step in the process is giving your computer the ability to read words. What does that actually mean? Well, the process is called tokenization, and again, there are libraries for this. Like I said, NLP has become extremely popular. Oops. Yeah, NLP has become extremely popular, and now there are libraries to do most of the things that you could possibly care about. So tokenization, again, we'll take a look at another library that's useful for doing this. And in particular, we're going to talk about this idea of subword tokenization. But I guess before I continue, into the low-level details of how tokenizers work and what they're doing and why they're important, are there any questions so far on transfer learning, on FastAI, on what NLP is about and why the progress has taken off so much in recent years? Let me see if I can pull up the Q&A over here. Okay, so there's one question from an attendee. It says, what process do you first use when training a language model? So download data, train, give test data, and check. Do we have to train the network each time we execute it, or is the trained data stored somewhere? Okay, so I actually closed the previous notebook, but let me just briefly answer that. The idea is you first download the data set you're interested in, right? So, and typically what you need is labeled examples. So in the case of IMDb, we had examples of the plain text review and a positive or negative sort of binary class for that. So the first thing, you need to do is download the data set, and then you typically train a model on that data set. The data sets, in general for machine learning are split into what's called a train, a dev or a validation set, and a test set. A training set is the data you use to actually train your model. A dev or a validation set is the set you use to check that your model is working, and these are typically examples that you can view. So you use them, kind of to figure out what's going on or what's going wrong in your code in case there are any errors. And then finally, the test set is supposed to be, kind of a set you use to validate that your model actually works in the real world. So these are models that neither you, the developer, nor the model ever see. And these are typically stored on servers, and you kind of submit your model to someone, and they verify that your model works on a test set. And typically the test set, you want to keep it hidden so that people can't overfit to it, and it's supposed to be representative of real world statistics. So there's another question from Mega. I wanted to know if this transfer learning is only used for classification and generation. Is there is this other use of NLP that transfer learning can help in? Yeah, so transfer learning is useful for a lot of things. And actually, since there are a few questions, let me just actually go back to this notebook and reopen that image over here. So remember, so transfer learning can happen at many different levels. And in fact, in this particular diagram, each of these errors can be considered one quote unquote transfer learning step, right? So the first level of transfer learning is we're transferring the information that we learned from the Wikitext language model. So this is the language model that predicts new words on Wikipedia, and we're fine-tuning that, to predict new words on IMDb. So that, in a sense, itself is a form of transfer learning, right? We're transferring from one model over here that's trained on one data set to a model that we're fine-tuning for another set. So typically these steps are called pre-training, which is pre-training usually means training a large, massive model, and then the fine-tuning step. And the fine-tuning step means is, usually training the model on the data you actually care about and you're going to, actually use to deploy into the real world. So over here, we actually have two fine-tuning steps, and typically this is called fine-tuning on what's called a downstream task. And there are many possible downstream tasks. So, name entity recognition, like I said, classification, question answering, and briefly, in a moment, I'll show you this website that allows you to quickly, browse different models. And that also has, like a benchmark, and you can see what the common NLP tasks are. But yeah, so a language model is used for just text generation, and that itself is a useful problem, right? So as we saw, the AI dungeon is basically a language model with a few other things on top of it. And that itself is a useful task. But it turns out that the language modeling in general is one of the most useful NLP tasks possible, because if you have a language model, you can then have pretty much any other NLP model that can solve any of these other interesting problems like text classification over here, right? So language models work on unstructured data. You have, just plain text in and plain text out, but that's generally considered the hardest of all the NLP problems. If you're able to, the idea is if you're able to read text and, essentially like generate new text, that kind of means you understand the language, you have a model for the language, hence the name. And yeah, so, classification is definitely not the only thing you can do. It's one of the possible downstream tasks. And, but regardless of what your downstream task is, what people generally do is they find you in a language model, and then they use the new language model on the data they care about to fine tune for a downstream task, which is what we've done over here. If you actually run the code, of course, and I'm just acting based on examples that have already been run. So there's another question. If my input is audio signal, how can I process the data? Yeah, that's a good question. So actually, all the stuff I'm talking about here isn't specifically for just NLP models. NLP is of course natural language processing, but it doesn't. The models themselves are more general than that. And in fact, I'm going to show you something interesting when we talk about transformers a bit later in this talk. Um, uh, but yeah, the short answer is you can use very similar models for audio, since audio is also just a sequence, right? So I think beyond language, what's more important isn't that we're processing text, or we're processing something that has to do with human language. I think the more important thing is we're processing a sequence, something single like 1D sort of stream of tokens, of characters. And this is very similar to audio. So there are a few ways you could do audio. One is transform your actual waveforms into spectrograms. That's kind of an old technique. People these days do use techniques that are very similar to the NLP pipeline. But I mean, one thing I will say though is actually, let me see if I can pull this up. So one thing people have been discussing recently is the ImageNet moment for speech. So despite what I said about the models themselves being kind of indifferent to the type of data you pass in, mostly all this progress over here is on text data, and data sets like Wikitext, like Squad, like IMDb are typically what's used. And we haven't actually seen the same level of progress in speech and audio applications. So there's actually this recent article that I thought was very interesting. Not sure if I can find it over here, but it was essentially about there it is. Show I missed it. But yeah, so this article kind of breaks down different approaches that have been used in speech recognition, speech to text, text to speech, that kind of stuff, which is basically audio, right? Speech is audio. And this is kind of very well detailed. It goes way back and kind of lays out the progress in this field and how it hasn't actually reached the same level of performance accuracy as ImageNet. And I'll talk about that. I'll revisit this idea at the end of the talk again when we're talking about NLP's so-called ImageNet moment. But yeah. Hope that answers your questions. If there's anything else, just let me know. But yeah, a lot of these things we will revisit as we progress. And it looks like there's one more actually. Could you send the link I referred to just now? Do you mean this one? Yeah, I can. Okay. Let me just mark these questions. Okay. Yeah. And if I'll release the slides after this, I actually plan to have them open now. But it seems like the link for this particular presentation was pointing to another older presentation I made, so which is kind of odd. But I'll share a link to the slides after this talk somehow, maybe towards the end. And yeah, you guys can just follow all these links and see what's going on. Yeah. So okay, back to tokenization now. So tokenization, coming to the lower level aspects of NLP, tokenization is the process of, like I said, giving a model, giving a computer, giving Python the ability to read words. So when I say words over here, what I really mean is a string, right? So hopefully you all are familiar with the string data structure. It just allows you to store characters. It's fairly basic. And what a tokenizer does is it converts strings and characters into some meaningful numbers. And we'll talk about what meaningful actually is in a moment. But at the simplest possible tokenizer is actually, and I love this example. It's this is essentially these 3 lines of code kind of encapsulate what the simplest possible tokenizer is. So a tokenizer is something that converts words into numbers somehow, right? And all you need is numbers to pass into your deep learning model, because as we know, deep learning models can learn to do this process called feature extraction. So all you need to do is pass in very sort of low level information. You don't need to do too much pre-processing on top of your text. Ideally, I mean, the more you do, the better results you'll get. But in general, you don't need to pass in something really complicated into your model. You can pass in the raw text. But what we need is sort of a vectorized representation or some sort of numerical representation for the text we're passing in. Now you could pass in the raw ASCII or Unicode characters, but in practice, what we want to do is we want to pass in some sort of a number for each word, if that makes sense. And we'll talk about how to do that now. So the first thing is to kind of construct what's called a dictionary, and I think that's a great use of terminology, because you can actually represent this as a Python dictionary. And this is basically mapping between a word and its position in the dictionary. So if you take out your copy of the the Oxford English Language Dictionary today, you'll notice that each word kind of has a position, right? So some word might be on page 782, and another word might be on page 24. And what you can do is kind of organize every word you've ever seen, not across the whole English language, because there would be a massive number of words, of course. Instead, what you do is just take all the words in the data set that you have. So over here, our quote unquote data set is just a very small string over here. But conceptually, what you can do is like read in a file and pass in all of the text information that you have into a single string. And then you just call string.split, which is built-in function in Python standard library. And it's able to essentially, like, what did this do? It splits up all these this entire string into a bunch of words, and now you have a dictionary, right? You have the first item in the dictionary is very, the second item is long, and the third item is corpus. And actually, might be able to. Oh, so this actually isn't a code block. I was trying to run it. But yeah, never mind. But yeah, this is a very simple example of a tokenizer, because this does allow you to convert words into numbers, right? You take in a string of words, you split it by on space, and then you just pass in the index of its position in the list that you get as a result. So that's a very simple tokenizer, and I think it's a great example. But of course, in practice, things are more complicated than that. You can't always split by space. To start with, like, a space isn't a good model for what a word actually is. Sometimes words are split by hyphens. There could be complex punctuation things. And yeah, there are a lot of other, I guess, restrictions associated with just using spaces. So in practice, what we do is build a more complex tokenizer, and ideally a faster one, something that's not just implemented in Python like this. And it would essentially split words into things like this using slightly more complicated algorithms, using regular expressions to catch more of the some of the corner cases in punctuation and all that stuff. But yeah, it essentially just splits up a word, splits up a sentence or a text corpus into a lot of smaller words. And then each word in this collection forms sort of a list, and also called a dictionary or a vocabulary or whatever you want. And you just take each word and find its position. So you say it is the first word, or you can organize these in, like, let's say, alphabetical order. In practice, that's not a useful thing to do, but I'm just saying as an example. You could organize these in alphabetical order, and just kind of pick up the index, and that's number, and you can pass that number into your deep learning model, right? But you'll quickly find that using just words is not very practical, because as your data sets tend to get large, like for example, we saw the Wikipedia data set, right? Like, just think about how many words Wikipedia possibly has. Now, I don't know the number off the top of my head, but I know it's probably a lot. So this technique isn't very practical, just splitting by words, because you can end up with a very large number of words. And typically these words are, one hot encoded. What that means is, you take the total size of your vocabulary. Let's say if you have 10,000 words, you pack that into an array or a vector of the size of your vocabulary. So if you have 4,000 words, each word would be represented as an array that's 4,000 items long, and then it would have a 1 in the position where you actually have the word you care about, and 0 everywhere else. So this is a fairly common thing. you just look up one-hot encoding, one-hot embedding on Google, and you get some more information about that. You can maybe do that if you're not familiar with the area. You can do that as I'm talking about these, because that's kind of an important idea to understand. It just means that like I said, you're converting a sequence of words into a sequence of numbers, and in this case, you're translating the integer number into a one-hot vector. So one-hot vectors and integers are almost the same thing. They can represent the same type of information. It's just a different representation, because typically in machine learning, we want to deal with vectors and not integers. So, what you'll realize is that if you have a very large vocabulary, a very large number of words, you're also going to have very large arrays, very large vectors. These one-hot vectors that you're going to pass into your machine learning model are going to be extremely large. And that's a problem, of course, because, memory is limited, compute is limited, larger arrays means more processing, and that's not very fun, right? So too many words is a problem. So you can't really split by word. So the other solution is splitting by character. Just take every single character and treat that as a single item. But the problem over there is, it's going to be harder for the model to learn from a sequence of characters versus a sequence of words. And it's hard to explain this, like in a very specific way, but it makes some intuitive sense, right? If I were to give you a sequence of, very, disconnected characters, you have to sort of piece them together. You need some algorithm to piece them together to come up with meaning, right? So for example, if I say VER, if I just give you those three characters, that doesn't really mean a lot, right? There's very little meaning you can extract from them. But instead, if I give you, the sort of words chunk by chunk, then as soon as you see the word very, you know that it's associated with size, or like something, extreme. So you kind of have that extra semantic information. This is what it's called. So you have this extra semantic information if you pass on words instead of just individual characters, right? The character Y, for example, which I've highlighted over here, doesn't mean a lot in the English language, right? What does just a letter Y mean? Not much. But instead, if you pass entire words like this, you have at least some meaning, and it's easier to piece together, entire words as opposed to individual characters. And also the other problem is, when you're passing in when you're passing in words, what happens if you see a word that you've never seen before, right? That's sort of an interesting corner case. Maybe you've never seen this word in your vocabulary before in your training data set. This word just didn't exist, but you might actually see it in the real world, right? So for example, like names of, just like nouns that you've never seen before. Names, could be, new URLs, links. There's all sorts of stuff that can lead to unknown words if you decide to just train on words. So that's a problem, right? But the problem with character models, on the other hand, is, if you tokenize by character, you have very little information about each individual token. So also, let me just briefly clarify. A token is just a thing that you pass into your machine learning model. So over here, it is a token. And the tokenizer's job is to figure out at what level you want to tokenize. So do you want your tokens to be words, or do you want your tokens to be individual characters? This is a decision that you, as a researcher or a machine learning engineer or a machine learning practitioner, gets to make. And essentially, yeah. So you can choose character models that choose individual characters and sort of piece them up together, or you can choose word level models that take entire words. That leads to a large vocabulary, and you may not be able to handle unknown words. So actually, recently, an interesting development that's happened is the rise of subword tokenization. And yeah, so subword tokenization is kind of like a nice sweet spot in between them. So on one hand, you have character level models that essentially just look at each string and split them by character. And you have word-based models that take entire words. And this can quickly lead to a large vocabulary size. So for example, over here, faster, fastest, and quickest all mean very similar things, right? They have similar meaning, but each of them is going to be represented as a completely separate token. And that's less than ideal, because as I said, with a large number of words, some of them can mean the same thing. So you can potentially save on some memory and some storage space, but there's no way to do that with word level models. So instead, recently people have been developing subword tokenization algorithms, And this lets you, like I said, come up with this nice intermediate representation instead. So you don't split words by, entire word chunks. You don't split them by characters, but instead you split them by the most frequently occurring subwords, or, the most frequently occurring sequences of bits in the actual, Unicode or ASCII representation. So there are a lot of interesting algorithms, and there's a lot of interesting details on how these work and how you can get them to perform well. And I'd encourage you to check out these links if you are inclined to. These are all just the research papers. But the idea is subword tokenization is another very sort of important improvement that led to all this progress that we were talking about earlier. So a lot of this process is again automated by the Hugging Face tokenizers library. So these algorithms that I mentioned over here are complicated, but you don't really need to worry about the exact details of how they're implemented, because all you need to do is pip install tokenizers, and Hugging Face has most of the stuff taken care for you. Again, I'll leave the specific code examples for you to look at yourself. But at a high level, you import different types of tokenizers from the library, and you can just use them directly. And let me, as a side note, let me mention that this is kind of important because a lot of modern models that you might be working with, for example, like BERT, Roberta, GPT-2, all these things usually work with only a specific tokenizer, and Hugging Face tokenizers implements most of them. So if you want to work with a BERT model, you have to use the BERT specific tokenizer. So that you actually feed in tokens that the BERT model recognizes, and Hugging Face automates that for you. But let's see if we can. Okay, yeah. So this maybe isn't the best example over here, but this is kind of what this one particular model can, this one particular tokenizer, can do. So over here we're using something called byte pair encoding. This was used in GPT-2. I'm not sure if it's used in GPT-3 actually. But yeah, byte pair encoding is one of the algorithms for subword tokenization that allow you to come up with this sort of intermediate representation that kind of groups together the most frequently used words. But whenever something is unique, it sort of breaks it off into its own new token. So the advantage again of the intermediate representation over here is that you can have the advantage of character level models where you're able to recognize every character, right? And so like most subword tokenization algorithms can recognize every character that you throw at them, and you also have the benefit of word-based models because the most frequently occurring word groups over here are bunched together into a single token. So it allows you to save on some memory. It allows you to also capture more semantic information about the sentences that you're passing in. So this is one example of what the tokenizers library does. Again, fairly straightforward, few lines of code. I'm not going to go through the details because Hugging Face documentation is amazing, and there are also plenty of tutorials on this already. But yeah, so this is sort of an output that you'd expect from a subword tokenizer. You can see that most of the words are actually recognized as entire words. So this is these are all fairly common English words. So they probably got grouped together in the optimization process for byte pair encoding. Input to be all those are fairly common words. Oh, also input actually got broken up. So sorry about that. So input got broken up to input. So you can see how input are both very common, but maybe input is not the most common in let's say like the Wikipedia dataset. So input got split up into two subtokens, but putting them together, you can kind of it's easier to sort of get the meaningful information about input. If it's in 2 chunks as opposed to 5 chunks, right? Another I guess model for understanding how this works is imagine if you and I were doing some sort of we're setting up some sort of communication scheme, right? You're sending messages to me, I'm sending messages to you. Would it be easier if and let's assume that there's a very large latency in the communication. So if I send a message to you, you only receive it after 10 days. So would you prefer if I send messages in entire chunks, like in entire words, or in individual characters? Definitely sending, if you can, batching up multiple characters together into words and sending entire words instead of sending individual characters is, much faster way to communicate. And it's kind of like an analogy for how this particular system works. But that's enough for tokenization, I guess, for now. Um, and I also noticed that there were a few questions. I guess let me take a look at that. So what is IMDb? So IMDb is a movie review site. Let me pull this up. Yeah, so it just it has a bunch of stuff about movies. People review it, and the IMDb dataset in particular is it's just this. It's a set of reviews that people have written on the site. These are all, I think, by critics. I'm not sure the exact details of this dataset, but the IMDb dataset consists of a bunch of movie reviews, each labeled with either positive or a negative class. And yeah, so the a common task is trying to predict in a sentiment analysis, right? In NLP. So given word or a sentence, can you predict the general sentiment, whether the person writing it was happy, sad, angry? The IMDb problem is kind of a reduced version of that. Yeah, so IMDb is just a data set, contains positive and negative text reviews from the IMDb site. That's short version. Can I explain one-hot encodings? Sure. So one-hot encodings, let me see if I can pull up a diagram. I was actually going to talk a bit about that now with embeddings. But at a high level, one-hot encodings is basically a way to convert an integer into a binary array, right? So let's just say that the size of your one-hot embeddings are 10. So what you do is you'd have an array of length 10, and each element of that array either has either a 1 or a 0. And if the number you want to encode is, let's say, 5, what you do is you'd go through that array, and then at the 5th index of the array, you would put a 1, and all the other elements would be 0. And it's called one hot because there's only one element in each array that's going to be a 1. Everything is going to be a 0. So that one element is kind of considered hot, while the other ones are cool. Not sure where the terminology came from, but yeah, I think I'll have a small visualization of that in a moment. Okay, so you mentioned how speech and audio is not developed as quickly as written text code. What is the industry focusing on developing for the same? Towards the end of the discussion. Sure, I mean, I can answer now as well. So I think, what is the industry focusing on? So, I mean, I think like in general, a common trend you'll see is that a lot of people are applying this one particular model called a transformer to a lot of different things. And I think one of the next things I'm going to talk about is the transformer. So yeah, this is a little bit of an interesting discussion to have that, and we'll talk about that in a moment. But I think, yeah, that's one important trend is transformers, right? So people are applying the transformer model to basically everything, including speech. And the article probably that I shared before does a much better job of laying this stuff out than me. I'm personally not too involved in speech-based applications, but again, yeah, it's very similar to NLP, and I think the most important thing is having the sort of to have the dramatic progress that NLP has had, like the written texts have. You need transfer learning to work in speech, right? So I think the single most important thing that could help is better data sets. So I'm not sure if there are, that many. So there's the Mozilla, I think, open speech data set. That's great. But I think we need, larger, more diverse speech data sets to really get, audio applications off the ground and, get them to work as well as NLP does. So, I mean, to be fair, like speech recognition is great, right? So like, like the Google Homes and Siris and Alexas, all those like work reasonably well today. But what I mean when I say that it's not at the level of NLP is like, we're not seeing like this, crazy exponential progress where people are just, sort of publishing papers left and right, and the field is advancing very rapidly. If you look at the speech recognition leaderboards, I think there's been considerably less progress than NLP. So yeah, that's what I meant by that. And also, I mean, if you want to, we can talk a bit more about that at the end if you'd like as well. Okay, and it seems like there's also some other stuff on the chat. Okay. Okay, so it looks like I've missed some of these that probably don't make too much sense to answer now. But yeah, let me just quickly say, what is an epoch? An epoch is just one pass of training. So that means when you're training a deep learning model, you give it examples of the data set, and you say, look, here's the input, here's the output. Can you learn what the relation between the input and output are? One epoch is when the model has gone through the entire data set one time. So typically you train for like, I mean, the number of epochs you train for can actually vary quite a bit between application to application. But one epoch is essentially doing one pass through the data set. Okay. In this figure, how can we calculate the number by separation fastest? Okay. So yeah, so remember the tokenization process is very similar, right? Like the only difference between subword tokenizers versus character and word-based models is how they decide to split the text into tokens. But once you have tokens, it's essentially the same, like finding the number is the same process for everything, right? It's how you actually decide to split the input text into tokens that matters, and that's what subword tokenization handles for you. The rest of the process is very simple, right? You have a list of tokens, and if you want to find what the corresponding number is, you just kind of organize them in a list and just pick out the index of that element in the list. That's a fairly standard problem. Okay, cool. So I realized that I'm not really sticking to the original time that I planned. So maybe I'll skip over embeddings a little bit. But again, high level stuff. Tokenization helps your model read words in the sense that you pass in raw text. So the input is raw, strings of raw text, and the output is just a bunch of integers or one-hot embedded vectors that kind of let the model work with numbers and identify what the word is. But that's not enough, right? If I just give you the index of a word in a dictionary, and if I asked you like comprehend language from that, it might be pretty hard, right? So if I just say like 742, 7,089, then you'd have to look at the dictionary each and every single time and kind of think about what the word means, and it's generally harder to reason about. So the next step in the pipeline is creating what are called semantic embeddings. An embedding is actually it's fairly detailed, so I'm gonna have to skip over some of the details over here. But this is again a low-level detail, and I think this article is again an extremely great resource. Since some of these links aren't going through, let me just share that now. So you can take a look at this article, and I think this is one of the best. Jay Alamar is an extremely great educator. He has a lot of fantastic articles that I'd highly recommend. Very specific to NLP and very specific to modern state-of-the-art stuff. And yeah, the GPT-3 article is great. He has one on transformers that's great. One on transfer learning. So yeah, all these are great tutorials, and I'd highly recommend them. But for now, what word embeddings do is they convert again words to embeddings, embedding vectors, but vectors that have meaning. So and over here, another minor detail for those that care is that I'm using the words array and vector interchangeably. Technically, they're not the same thing. Vectors have some sort of specific mathematical meaning, but I think that's a minor detail, and we can, for all practical purposes, they're the same thing. So I'm using those ones interchangeably. But yeah, so what Word2Vec and other embedding algorithms do is they take in the words, and when I say word over here, what I really mean is the one-hot vector. So tokenization has already taken care of the process of converting this string, these actual physical characters into a number. And what you need now is a mapping from that number or that one hot vector into another vector that carries some more meaning about what the actual word is. And actually, in the interest of time, I'm just going to say, you can check out this article. It's great. But at the end of the day, I think what's important is after the word embedding process, what you actually get out from this entire model is you get a sequence of let's see if this is visualized somewhere. Yeah, so you get a sequence of vectors like this. So previously, I mentioned that the one hot vector has a single element that's 1 and everything else is 0. The embedding vector has just general floating point numbers over here, and these numbers put together actually have sort of they're able to convey meaning as to what these words actually mean. And this is actually a very surprising, interesting fact. This is one of the things that excited me the most about NLP is just think about that, like words, English words, and not just English, like any language words can be represented in some sense as vectors. And you might think it's a little odd, words convey more meaning than numbers possibly can. Sure, but I mean the important thing is we're actually able to using this model of mapping words to vectors, we're able to create a lot of interesting and useful applications, which kind of sort of highlights that it does work in some sense, right? But yeah, word embeddings. If you take anything away from this, let me just say, what you need is something that does this mapping, right? So both in tokenization and embedding, at the end of the day, you need something that can convert words into vectors, like raw text into vectors that contain some meaning. And it might be a little hard to wrap your head around the idea that this mapping is even possible, and that words can be represented as numerical vectors that we pass into a deep learning model. But I think the evidence is there in the fact that all the interesting things that we've been doing with NLP actually work, right? So maybe we can revisit the idea of embeddings, and we can talk a bit more about it because they're certainly interesting. We can talk a bit more about this towards the end of the talk if people are interested. But for now, I'm just going to leave it at that. Word2Vec is one of the most popular algorithms for doing the tokens to embeddings mapping. So just to recap where we are, we started off, like previously with explaining what transfer learning was. Transfer learning is just at a high level is the single most important process that you need to know. So if you take away one thing from this, if you say I only have scope for implementing one thing to improve my NLP pipeline, my NLP process for my organization, transfer learning is that most important thing. So even if you don't do sub-word tokenization, if you don't do Word2Vec, if you don't do any of the other things I'm going to talk about today, definitely do transfer learning. That's the most impactful advancement. Yeah, so from there, after discussing the high level stuff, we talked a little bit about tokenization. Tokenization is the process of mapping words into tokens, right? And then from there, you map the tokens into embeddings. And yeah, embeddings are just vector representations of words, visualized over here. This article does a great job of explaining it. But yeah, at the end of the day now, after all this discussion, what we have is we have some function that can take in words and it can spit out vectors. And that's useful because as you know, deep learning models, they love large vectors, matrices, arrays. And this is sort of the right representation to work with. And now we can actually pass something into a deep learning model to do useful stuff, right? But now let's jump ahead a little bit. What is the deep learning model exactly doing? And typically, like maybe 6 or 7 years ago, the most popular, the most common architecture, the most common type of model being used was something called a recurrent neural network. And different variants of this is not just the recurrent neural network. Is there's this thing called the LSTM. As we showed previously in the Fast AI notebook, there's a variant of that called the AWD LSTM, and there are all these different variants. But fundamentally, it was based on this idea that you read one word at a time, you do some processing on it, and then you generate a new sort of representation, a new output. I mean, maybe you can call it a feature map or a feature vector, however you want to consider it. But if you're familiar with, like the most basic type of a neural network, it takes in some data and it's able to build an intermediate feature representation of it, right? So RNNs kind of do that through time. So you take in a word, you process it, generate an embedding, you pass that embedding into a single RNN layer, it generates an output. Then you pass in the next embedding corresponding to the next item in the sequence. It generates the next embedding and generates the next embedding, so on in a loop, right? And I think that's the most important detail over here, in a loop. So RNNs, they work in loops, and you essentially do the same computation over and over again, and it explicitly requires a loop. And that's important because you can't, parallelizing RNN computations is a little bit harder. So transformers was, the specific, it's this one architecture that came out in 2017. And I mentioned before that, transfer learning is the most important thing. That's what you should do if there's one thing to take away. Transformers are like the second most important thing. So, if you recall the graph that I showed you over here, yeah. So over here, out of all of these models, everything beyond Elmo is actually a transformer. So transfer learning is great because it allows you to leverage all these models, right? And that's important. But if you look at what these companies are actually training, they're all training transformers. And I'm pretty sure that every single one of these is a transformer. And just to expand some of these acronyms, because I found that to be useful as well. So GPT stands for, not sure if you guys can see this clearly, I'll zoom in a bit. GPT stands for Generative Pre-trained Transformer. BERT stands for Bidirectional Encoder Representations for Transformers. I mean, these are all fairly complex sounding words. But essentially what I'm trying to say is that all of these are transformers, right? Roberta is a version of the transformer, is a version of BERT. XLM is another variant. XLNet is a variant. DistilBERT is another variant of BERT. There's one called Transformer Elmo, which is basically Elmo for transformers, I guess. And the last one over here shown on this chart, Megatron, is also a transformer. So all of these are transformers. And the reason I think that all these companies love training transformers is that they're very easy to parallelize, right? So the transformer architecture is actually kind of similar to the RNN, in the sense that RNNs, they were actually there since the 1980s. The RNN architecture is very old, and even the modern, so-called modern variants of the RNN, the LSTM and the glue, these are also fairly old architectures. The LSTM was invented in the 80s, and the GRU architecture, which is another RNN variant, was, I think, came out in 2013 or 14. Don't quote me on that, but yeah, these are all fairly old, and they've had a lot of time to mature and develop, is what I'm trying to say. And one of those advancements that came along with RNNs was, at some point, was something called the attention mechanism. I'll talk about that in a bit, but an attention mechanism is essentially a layer. So you're familiar with how deep neural networks have multiple layers, right? Attention is just another layer. So out of all the layers, you stack, recurrent layers, which are what RNNs are primarily composed of. Then between RNN layers, you could stack what is called an attention layer. And let's get into what attention layers actually do and what they mean a little bit later. But what transformers fundamentally did was they removed the for loop. So I mentioned how the kind of most important detail to remember about the RNN was that it does processing in a loop. So it takes in an input word, it does some processing, produces an output, it uses that output to generate the next input. So it's kind of this forward dependency over there. You need the next word, you need the next output, you need the previous output, sorry, to calculate the next output for an RNN, for a recurrent layer. But RNNs had both recurrent layers and attention layers. So another advancement, the main thing with transformers was actually somewhat backwards. They said, let's throw away all the recurrent layers. We don't need them. So the name of the transformer paper actually was, the name is, this is one of the most I guess interesting and popular names now. Let's see if I can pull up the original paper. Yeah, There we go. So the paper was titled "Attention is All You Need," and the same sort of naming structure has been used for a lot of, perhaps it's been overused in NLP literature these days. So, but yeah, there's a whole culture around this sort of naming. But yeah, I mean, essentially, the core idea of the transformer architecture was, let's remove the for loop. Let's remove the part that makes RNNs slow, and not exactly slow, but not parallelizable. And let's instead do let's instead use just the attention mechanism, which is parallelizable. And at the end of this talk, when I'm going to tell you a bit about the power architecture and how it leverages CPU and GPU, super fast interconnect between the CPU and GPU. This is why that kind of stuff is useful, because when you're training transformers, you have this, since you can run everything in parallel, you have this demand of you need to be able to transfer large amounts of let's say like weights, data, gradients in the training process, between the different devices very quickly. And this wasn't that much of a problem for RNNs, right? So with the RNN, you didn't need a massively parallel compute cluster, because the fundamental limitation was the for loop. You needed the previous output to calculate the next output. But with the advent of transformers now, we're able to leverage the compute we have much better. So you'll note that one of the largest models over here was trained by NVIDIA. NVIDIA makes GPUs, and GPUs are fundamentally parallel processing units. So they allow you to perform a large number of very simple mathematical arithmetic expressions extremely quickly. And the power architecture, right, is one specific development on top of that. So it's kind of like this, it's a CPU architecture, but fundamentally a lot of things need to go through the CPU before they ever reach the GPU. And vice versa. In general, you need to communicate different things between the CPU and GPU. And if you have the GPU that's able to perform all of this crazy, complicated transformer arithmetic, which happens in parallel, if you're able to do that very quickly, but you're bottlenecked by your CPU's performance, which processes things serially with a fairly small, relatively smaller number of cores, then that could be one potentially important bottleneck. And also transferring data between the two is in general very slow. So you don't want to use your CPU for communication. You instead want to just use it to kind of control the GPUs and let the GPUs do all the hard work. So to do that effectively, what the power architecture does is, at least from my understanding, one of the most useful features that's in my research has been the fact that it has this very fast interconnect between the CPU and GPU called NVLink. And it was one of the first architectures actually to leverage this technology, and this allows you to essentially leverage all this parallelism that GPU is giving you in a much better way, which allows you to train transformers much better, as opposed to RNNs, which the sequential models. Now we can train transformers much faster. Okay, but the transformer architecture really other than transfer learning, which I think transfer learning perhaps doesn't get enough credit, but transformers certainly do. So let's just take a look at this website, and this is what I alluded to earlier. I just pulled up this link over here. This is Papers with Code. It's a website where actually let me just go back for a second. So Papers with Code is a website where people post their research. So it has a bunch of links to research papers and the results. In general, it makes it easier to look up benchmarks and tables and find new research papers and see what people are implementing. And also, as you can infer from the name, Papers with Code implies that all these papers generally have some sort of code implementation. So it's all too common to have papers that are just purely academic and they never release their code, and so no one knows how to train the model in practice. Papers with Code is kind of trying to solve that problem by making it easier for people to find implementations of the most popular repositories. So what I'm going to do now is quickly open Papers with Code. And this is the homepage. I haven't done any crazy search queries. But what I can guarantee is that on the front page, we are going to see some paper that uses a transformer. And you can trust me on this. Like, you can pull up this link yourself if you want to. Let me share this link over here. Let's see. Yeah, so that's Papers with Code. Check it out if you're interested in deep learning research. But even if you're not, I encourage you to just go to that link right now and see what's trending and see what the latest papers are. There's guaranteed to be something with transformers. Oh, and look at that. If you look at the latest papers, there's something published today that has that uses a transformer in some setting. Over here, vision. So like within the last year, using transformers with vision has also become popular. And like I said, the reason transformers work so well and are widely accepted today is because they allow us to leverage the powerful compute that we already have. So they're massively parallelizable, and when you have systems like the Power 9 chip, which is run the AC 922 server, which is what a lot of actually academic clusters today have. When you have this sort of massive parallel scalable compute, then using a model, using an architecture that leverages that is very important, and allows you to make the most of your hardware and train massive, huge models to perform all sorts of interesting applications. So over here, the transformer architecture, if you're interested in the specific details of the transformer, there are thousands of articles on the internet. I don't want to spend time explaining that over here, but the transformer essentially it's the most important detail about transformers is that they're very easy to scale and they're very easy to parallelize. So they allow us to leverage a lot of compute and scale to very large transformers. And like I said, typically larger models gives you better performance, right? So transformers have taken the world by storm and have been implemented for like all sorts of crazy tasks. So over here we see the vision transformer, but I guarantee that there's going to be at least a few more. Okay, let's see. So there's one based on attention maps. Attention and transformers are kind of synonymous now. Let's look at what's trending. Okay, there's something about transformers over here. In fact, this is about GPT, so that's interesting. There's another variant of a transformer over here. There is, yeah, another variant over here. So you can see this is just one particular architecture, but it's so successful because it allows us to leverage parallel computation that is being applied for basically everything these days. And one could argue that maybe the whole transformer trend has been overdone a bit, but yeah, it's probably here to stay. And people are training ever increasing transformers. And also, Papers with Code, one of the most useful features of the site, I think, is it allows us to see what the actual state of the art is. So you were asking, I think someone was asking previously what the other types of things you can use transfer learning for. Well, here's the list of all the things you can use it for. Pretty much every NLP task that you can think of. You can use it for machine translation, question answering, language modeling, of course. You can use one language model to fine tune another language model. You can do text classification as I showed before, sentiment analysis, which is kind of a variant of text classification, text generation, which is essentially the same thing as language modeling in some sense, but is also more useful for like dialogue bots and chat bots and dialogue agents, that kind of stuff, like how we saw in the demo earlier today. Yeah, you can use them for summarization, named entity recognition. But let's look at the language modeling leaderboards, because as I said, language modeling is probably the most important and useful NLP task. And let's also maybe do machine translation, because that's a very relevant application in the real world. And notice now that every single, like almost every best method for these particular data sets, and these are all the most common data sets for whatever this task is, all of these, almost all of them are transformers. So there's Megatron, which is transformer. So also just quick note on Megatron, it's this sort of massive language model. It's been surpassed by GPT-3. So GPT-3 is now, I think, the world's largest deep learning model with many trillions of parameters. But yeah, these sorts of models are not things you would be training or even fine tuning on, to be honest. They're still very large, and they're kind of reserved for the elite who have access to that sort of massive compute. But yeah, using something like GPT-2 or Transformer XL or BERT is probably much more common. I think BERT and Roberta are probably the most common. But notice how every item on the list over here is basically a transformer, except for this one, which is some new LSTM that I haven't heard of. But the leaderboards are dominated by transformers. And even over here with machine translation, I see transformers everywhere. But yeah, transformers are extremely popular now. It's a huge trend, and it's all based on the idea of parallelism and this thing called the attention mechanism, which I wanted to talk about a bit now. So I actually previously gave a talk about attention mechanisms, and I think there's a recording available, so you guys can check that out. But the attention layer in the transformer network is this is the single most important thing for the architecture that has dominated all these leaderboards that I was just showing you now. And it's kind of apparent from the name itself, like the title of the paper. But pay attention. Attention is all you need. Kind of implies that it's an important thing to look at. So I thought it'd be useful to spend a few minutes talking about this. So again, don't want to spend too much time on this because I've talked about this before. You can also check out my slides for this, I guess. Let me share a link to that. Okay. Yeah. So just briefly, since there are some useful diagrams over here, I just wanted to bring this up. So an attention mechanism does a few fundamental things. It routes information between different components of the input. It captures global features. So global features means if you have a sentence or a document that's very long, it's generally hard for recurrent neural networks to learn features that are, you might mention, for example, a name. So let's say you're writing like a legal document and the letter is addressed to someone, and then only pronouns are used for the entirety of the article. And then towards the end, again, you have like a space for them to sign. So you have their name again. It would be hard for a regular model to learn complex dependencies that span the entire document. So but attention mechanisms help with that, and they also help with interpretability, which is basically making machine learning models easier to understand. Again, not too many details over here, but this is like this nice visualization on what attention layers can do. It gets its name attention because this layer kind of tells the network what to focus on in some sort of an abstract sense. So over here, you can see if we, after this particular example is for an image captioning model. So it takes in an image as input and it generates a caption over here. The captions are realistic and that's great. But another thing you can do is sort of use the attention mechanism to look at a specific word and point to the corresponding point in the input that activated it, so to speak. So you can see over here that using attention mechanisms allows us to kind of capture interesting information and understand the models we're training better. But yeah, so another keyword if you want to look this up is multi-head self-attention. This is the one implemented in the transformer. But yeah, I'm not going to go through all these details now. One important thing though is that attention and a variant of it called self-attention are not computationally cheap. So they do leverage parallelism, and that's great, but they're still extremely memory hungry, right? So just as an example over here, self-attention, the way it works is it draws dependencies between each position of the input with each position in the next stage of the input. So let's say you have a 1080p image over here, right? This may be a common example that you might get from a cell phone camera. Again, if you want more of the details on what exactly is going on here, I encourage you to check out this other talk and also my slides for this one. But let's say if you have a 1920 by 1080 image, if you want to draw dependencies between each number with every other number, you're going to need the square of that. So the self-attention layer has an n square memory complexity. That's one important thing to know, and it can get pretty expensive, and the computation becomes a real hassle when training networks, large networks with self-attention, because the longer the input, n square of the input basically means that when your input sequences get very long, it can be very hard to train your network due to memory constraints and all that. There are some potential solutions. Not going to discuss that now, but also GPT-3, the language model that I talked about before. This one in particular has 175 billion parameters, which is much larger than anything we saw over here. Let's see if we can pull that up. So yeah, I think Megatron had, it was just 8.3 billion parameters. This one has 175 billion. So OpenAI really spent a lot of money in GPU time and compute time to make this thing work. GPT-3, like I said, is not very practical for us to train ourselves or even fine tune. And this is an example of that. Forget about fine tuning. This thing requires 22 GPUs just to run inference. So if you want to make a single prediction with OpenAI's GPT-3 model, while it can do amazing things like the AI Dungeon demo that we showed you before, that actually runs on GPT-3. And the way OpenAI is doing this now is that they have API access to the language model. So you can't run it yourself, you can't download the model and run it, but it's behind a paywalled API. So you can get access to the API. I think you pay per query or something. And that's what AI Dungeon does. But it requires 22 GPUs, for inference. It's not very fun and easy to run. So there's a lot of very complex engine. It's truly an engineering feat that this model even exists, and the scaling even beyond this. So GPT-4, who knows how many parameters that's going to have, but if the current trends are anything to go by, it's going to be very large and very interesting. Okay, but yeah, that's a bit about attention mechanisms. Again, if you ask what the most important idea is, it's that transformers are a very powerful architecture. They've been used for a lot of things across different domains. And the core sort of layer, the core mathematical operation that's happening inside a transformer is the attention layer. Okay, so now I also want to briefly talk about, I think this is the really fun stuff, is what made NLP actually work? Like, why did we get this, exponential progress shown in this chart over here, right? And, the transformers and, transfer learning really do explain most of them, especially when you combine the two of them together. So, a lot of people have described this general trend of exponential progress and how things are improving so fast as the quote-unquote ImageNet moment. And there's a good reason for this. So I don't remember the exact year actually, but when Dr. Fei-Fei Li from Stanford released the ImageNet dataset, that was one of the most groundbreaking moments in computer vision, because everyone had a standardized dataset to train their large models on. So remember how, in transfer learning, the first step is you train a very large model on a fairly standardized task, and usually someone else takes care of this for you. And then you fine tune on the application that you care about. And this has actually been happening for a while in computer vision. So when the ImageNet dataset came out, like pretty much everyone started training on this. All the research labs, all the big companies were training pretty much exclusively on ImageNet. And then from there, everyone was implementing, everyone had like the pre-trained ImageNet models, which is kind of like the pre-trained transformers today. Everyone had the pre-trained ImageNet models, and they would just do fine-tuning on top of that, and that made computer vision extremely successful. And similarly, what we're seeing now is, there isn't, I don't think it's because of a data set in particular, but because of the general idea of applying transfer learning through this process of fine-tuning a language model and then fine-tuning on a downstream task, that in combination with the idea of the transformer architecture and the attention mechanism, those two things, the transformers and transfer learning, are really what created the so-called ImageNet moment. So yeah, ImageNet did the same thing for computer vision, transformers, and transfer learning since I think like roughly 2018. So 2017 was when the transformer paper came out, and by 2018 it was kind of really getting traction. And I think 2018 was when GPT-1 came out, like the first GPT from OpenAI, and that was, I think, a big milestone, because that was the first, I believe it's the first work that combined both transformers and transfer learning. So the attention is all you need paper was 2017, and roughly at the same time, I think purely by coincidence, transfer learning was also becoming a thing. OpenAI combined the two together, and since then, magic has been happening. There's this website called NLPprogress.com, run by a researcher from DeepMind, Sebastian Ruder, and it has information about what the current state of the art is across all sorts of tasks, and it's been growing extremely quickly. So also these are some of the most common. Well, it's a bit more extensive than the most common tasks, but yeah, there's a fairly detailed list of all the NLP tasks across the different languages as well. So it's important to recognize that all the stuff I've been talking about for NLP is for natural language, and natural language isn't always English, right? It encompasses a whole suite of languages. And yeah, this is, I think, is a great website for tracking progress in this field. Yeah, but I think you get the results of what happened since the conception of the site, I believe. And you can see this, if you kind of, if someone was to plot a graph of all this stuff over time, it would be very interesting to look at how all these things kind of, in parallel just have this sort of exponential trend. They keep getting better, and they keep, a lot of them probably use transformers and transfer learning. So it's actually, just take a random example. Let's see, maybe something non-standard, just so we can see if this hypothesis of transformers and transfer learning holds true. Let me just take part of speech tagging in Vietnamese. And there we go. Like I really didn't plan that ahead of time, but apparently Fobert Large and Electra, apparently these are the best performing models for Vietnamese part of speech tagging. And both of those are transformer-based models. So, I don't think that's a coincidence. And yeah, so, I think at the end of the day, the single most important thing that I wanted to convey in the talk is, NLP is here, and like really good NLP is being deployed today. We've had a lot of crazy progress over the years, and fundamentally all this stuff, all the stuff that you're seeing on the graph boils down to two very simple things: transfer learning and transformers. And if you want to get working with all these technologies, some of the things, lower level details you need to understand are how tokenizers work, how embeddings work, how to build transformers yourself in PyTorch, and but also leveraging libraries like Hugging Face to take care of some of the heavy lifting for you, and how attention mechanisms work, because they are the single most important layer in the transformer architecture. Okay. With that, I'd also like to thank Ganesh and the Open Power Foundation for providing their compute infrastructure to help us run a bunch of experiments. I don't think there's too much time to talk about some of the research that I was doing, but if anyone has any questions on that, I'd be happy to answer it. I think, as I alluded to before, right, one of the most important things in deep learning today, this has been true for maybe like 10 plus years now, is that we need parallelization. Models are getting larger and larger, and the trend isn't going to stop anytime soon. And even the simplest models today, it doesn't have to be something like GPT-3 scale, but the simplest models today also usually run on GPUs, and that's the infrastructure you need to run these experiments. And the Power 9 chip, which I think co-developed by IBM and the Open Power Foundation, as well as a few others, really helps you accelerate that through improving the parallelization by having a very high bandwidth interconnect between the CPU and GPU via NVLink. And this allows you to run all sorts of crazy experiments much faster than you could on other architectural hardware. And also, if you guys would like to hear more about NLP and all the stuff I talked about today, I have a book coming out. This is co-authored by me and Ankur Patel. It's going to be published by O'Reilly this summer, and that has a lot of detailed information of basically all the stuff I talked about here, but in much more detail. We walk you through everything from scratch. And yeah, with that said, I guess I'll now leave it open to questions, and also the quiz that I think Vaibhav has shared and prepared.
Thank you very much, Ajay, for the wonderful presentation for the last, I would say, like nearly 2 hours. Definitely, the people who were part of this meeting, the webinar, would have got benefited actually. I already see some messages, on the chat window about the presentation. You really took us, a deep dive on, the NLP from the low level to the high level. Very interesting.
Sure. Thank you.
Yep. And I have, people from the panel. Panelists, any questions for Ajay? And also audience, if you have any questions, direct questions, you can raise your hands so that I can open up the audio for you. Any questions? Looks like Ajay already addressed most of the questions through the chat window.
Sir, one question here.
Yeah, go ahead, please.
Okay, so it was a great session. Thank you, sir. My question is, if we have only self-attention network and not like only a single self-attention network, will it benefit parallelism in a transformer kind model?
So okay, let me just briefly say, while the attention mechanism is the most important layer in a transformer, it's not the only layer. So I think if you just have the attention layer alone, you'll actually just get a linear model, which would be like very similar to I think doing linear regression or something like that. You need activation functions, you need multiple stacks of self-attention layers, and you also need feed-forward layers. So there are actually a few different things going on in the transformer architecture. I think I had a, yes, so in this presentation, actually I had I think a diagram somewhere here that shows, or I guess not. But yeah, I mean, so you can look up the diagram for the self-attention model, and you can see that there's actually, sorry, the transformer model, and there's actually a few other layers other than just the self-attention. I don't think a single self-attention layer is enough, but what I can say is if you use just self-attention and like other similar layers that are embarrassingly parallel, as it's called, that don't have like this the next input depends on the previous input sort of dependency, then you get very good parallelism, and it's easy to accelerate that on things like NVIDIA's GPUs.
Okay, thank you.
Thank you, Professor Reshma. Thank you. Any other questions from the panelists and from the audience for Ajay?
Yes, sir. Good evening. This is Dr. Vincent. Very nice, wonderful. Hello.
Yeah, go ahead, sir. Go ahead, sir.
Yeah. A very wonderful presentation from 7:30 to 9:30. I think it's very useful for the researchers who is working on the NLP. And regarding the embedded, I think you talk about the accuracy. While talking about the cosine, it comes around some 82%. And some of the results you shown some 94% and 93%. What will be the best way to fix the level?
So are you referring to the notebook which I shared, the FastAI one?
Yes. No. Just how do you fix the value, the threshold value for the getting the best level of accuracy in our results?
Oh, okay, yeah, I see. So I think in the FastAI notebook, I actually didn't write that one myself entirely. This is an existing example in FastAI. So I'm assuming what the team has done over there is that they probably tried a few different values, did some basic level of tuning. But another thing I'll mention is that FastAI, like the people working on FastAI, have actually spent a great deal of time optimizing those hyperparameters and all those like minor details. So the learning rate, the dropout factor, this is all sorts of minor numbers that you have to tweak when training a deep learning model. What I found in my own research is that the FastAI defaults are usually extremely good, and it's very hard to do better than that by trying to come up with your own stuff from scratch. So while I'm not sure about the exact method they used to arrive at that number, since I didn't arrive on that particular number myself. What I can say is that since the process has already been done, it's useful in practice. If you're looking at what hyperparameters you want to use, I think the FastAI defaults are a great place to start.
Thank you.
Thank you, Mr. Vincent, for the question. Anto,
Hello?
please go ahead.
Yes, sir. So it was a great session today, and I'm just a student, and I want to start as a beginner. How can I start this NL natural language processing? Is there any roadmap or any process of moving in this field, like that way? Any kind of advices for me as a beginner?
Sure. Yeah. I might be somewhat biased here, but one potential way is my book. But I think so this book actually isn't written in time for complete beginners. More realistic ways. I can share some. In my experience, I think the single best resource for learning everything related to deep learning is the FastAI course. So this has helped me a lot, and I owe most of my deep learning knowledge to them. They're the ones who got me started on learning more about this whole field. So I'm sharing a link in the chat now. FastAI, I think honestly this covers like most of the stuff you need to know as a deep learning practitioner. So this covers like not just NLP stuff, but computer vision. I think mainly computer vision and NLP, and like also tabular data and stuff like that, entirely from scratch. This is completely for beginners. There are a few courses. They also have a library. So the library that I was showing you before in the notebook, right? That's also developed by FastAI. So they have a lot of great education programs. I highly recommend checking out their MOOCs. But also, I think another useful tip is like don't spend too much time with reading papers and like getting caught up in the details of the math. I think it's important to actually just implement things yourself from scratch. I mean, not just from scratch, like implement things in code. So actually have code that is running on your computer that solves the task you're interested in, as opposed to just reading about how the task could potentially be solved. Because you'll find that when running things you encounter all sorts of issues. As was just mentioned before. Finding those small values like the hyperparameters and like deciding that 0.8 was the correct value at some point. This is not a very intuitive and natural process. So
Yes.
and you only find those stuff once you actually run the code. So use high-level
Yeah.
libraries, Spacey, FastAI,
Yes.
Hugging Face, and yeah, I think it's a great place to start.
Yeah. Thank you so much.
Sure.
Thank you, Anto. Okay, I think we are almost it's going to be 9:30 here. So with this, I just want to thank again Ajay for his wonderful session for last 2 hours. I really appreciate it. And also, audience, there is a quiz, and please go ahead and answer the questions, whatever asked by Ajay. And definitely, you'll get an opportunity to work with us on our hardware, along with a T-shirt from our Open Power partners. And also thank you for the panelists, for spending time here and nearly 2 hours. And also some of you asked very good questions too. Thank you very much, and have a great day as well as a wonderful evening. Thank you.
Sure. Thank you for organizing this, and yeah, it was my pleasure to come and talk.
Thank you. Thank you.
Yeah. Thank you, sir.
Thank you.